Welcome to Heating Materials Lecture 16. In the last lecture I looked at blackbody radiation, briefly introduced the Lambert cosine law, and then shape factors for dealing with the exchange of radiation between two black bodies. Today I want to look at grey bodies and the radiation exchange between grey bodies, the development of an electrical resistance model to deal with this, and I'll show it in the context of a simple furnace example. And I'll also look at measurement of a temperature in a gas flow, which is an example of radiant exchange involving a small object in a large room. But before I do that, I want to look at the calculation I left you with last time. If you've not tried this calculation, you should stop now and have a go at it before you have a look at the answer. So the question involved a tube furnace with an internal diameter of 10 centimeters and a length of 25 centimeters, and you were asked to work out the amount of heat, radiative heat that will be lost to the two ends, assuming that the tube wall is uniform temperature, which would not in practice probably be true, but it serves to show what the effects of the length of the tube compared to the diameter is. So for the solution, the first thing that you need to do is to refer to the graph that looks at the radiant exchange between two circular surfaces. And if we do that, we can work out that the approximate exchange of radiation between the two ends, which would be F12, would be 0.004. In fact, if you use the equation that I also gave you when I showed you this graph last time, it turns out the slightly more accurate value is 0.037, but 0.04 would be perfectly adequate, and I was expecting you to use the graph. As we're dealing with an enclosure, we can then say that F12 plus F13, so that's the fraction of radiation going from one end to the other, plus the fraction of radiation going from one end to the side wall, must equal 1. Rearrange that slightly and we can work out that F13 is equal to 0.96, and you can see that I'm using the value from the graph, which is the one I expected you to use. We can then apply reciprocity, which would say that A1 F13 equals A3 F31, and a little bit of rearrangement that allows us to work out what the value of F31, which is the fraction of radiation going from the wall to one end. Obviously this involves the dimensions of the tube, so here we have pi r squared for the area of one of the ends, and here we have 2 pi rl for the surface area of the interior wall. Putting all the numbers in, that gives us a value of 0.096. We just need to multiply that by 100 to turn it into a percentage, and then by 2 to turn it into the percentage of radiative heat lost to the two ends, which is 19.2%. And that will seem like a relatively large number, and that reflects the fact that this is quite a short tube compared to its diameter. And if you want to minimize the radiative losses to the ends, you would actually want a longer tube for that sort of diameter, with a hot zone centered in the main central region.